This is the 9th video in a series covering ring theory. And today we want to look at UFDs and PIDs again, and we want to prove a classic result that every principal ideal domain is a unique factorization domain. And then we'll also dip our toes into the notion of a Euclidean domain. So throughout this video, I'll use the notation where D is an integral domain, so any type of integral domain. And now let's recall that D is a unique factorization domain, in other words, a UFD, if every non-zero non-unit A can be factored uniquely into irreducibles. And now that uniqueness is up to associates or up to multiplication by certain units. So I'll urge you to look back at your notes from previous videos where we defined in more detail the notion of a UFD. Okay. Then the next thing let's recall is D is a principal ideal domain if every ideal is a principal ideal. So in other words, every ideal is generated by a single element. That's what it means for an ideal to be principal. Then let's look at this new definition, which will be helpful for our main result of the video, and that is a commutative ring satisfies something called the ascending chain condition if for every chain of ideals I1, which is contained in I2, which is contained in I3, which is contained in I4, and so on and so forth, there exists a capital N, a natural number, such that for all little n bigger than or equal to this capital N, I sub little n is equal to I sub capital N. In other words, this chain stabilizes at some point and the ideals are all the same. So in other words, you can't have an infinite chain of ideals where they're all different. And just kind of BTW, a ring that satisfies the ascending chain condition is called the Noetherian ring. All right, so let's start with some non-examples of Noetherian rings. In other words, non-examples of rings satisfying the ascending chain condition. Let's start with this classic example, which is the ring of polynomials in infinitely many variables. And so you might recall that we've looked at the ring of polynomials in a single variable before. I think maybe we did one example, the ring of polynomials in two variables, but this is infinitely many variables. I'll call them x1, x2, so on and so forth. And now let's look at the following chain of ideals. The first one is generated by x1. So that's going to be all polynomial multiples of x1. But notice that that is contained in the ideal generated by x1 and x2, which is contained in the ideal generated by x1, x2, x3, and then so on and so forth. So we just add a new monomial at each stage, and the new monomial is just one of these kind of base variables, if you will. Now, I think it's pretty clear that this chain does not stabilize, so there's no point where after that point, the ideal is the same as everything before it up to, well, the stabilization point. And so that means this is a non-Noetherian ring. In other words, it does not satisfy the ascending chain condition. Okay, so let's look at another classic example. So here, I'm going to write this as C of R. So this is going to be the ring of continuous functions. And those continuous functions go from R to R. So you know some things inside of this ring, like the sine function, the cosine function, but also there's crazy things in this ring, such as piecewise functions that are glued together in a way that make them continuous. Okay, so now I want to define I sub n to be the following ideal, and that's going to be all functions f in CR, so all continuous functions satisfying the following rule, and that is that f of x equals 0 for all x bigger than or equal to n. So in other words, it looks something like this. So let's say here is 1, here is 2, here is 3, maybe just for good measure, there's 4. So an element of I sub 1 kind of does anything at once, but then it zeroes out at this number 1 and it's 0 everywhere else. So I'll just put here, this is the graph of a function inside of I sub 1. So I'm abusing notation there, but I think that's okay. And then a graph of something in I sub 2 would look something like this. It does whatever it wants until it gets to the number 2, and then after that it's always 0. So that's something in I sub 2. And then something in I sub 3 kind of does whatever it wants until it gets to 3, and then it's always 0. So that would be something in I sub 3. And then, well, you can kind of see where this is going. So I'll let you check that this is indeed an ideal, but I think it's pretty clear because essentially you're just multiplying by 0 after a certain point, which is just going to give you 0 after that point. That'll give you the absorption property of the ideal. The addition or the subring property of the ideal is also pretty easy. But I'd also like to notice that I sub 1 is most definitely contained within I sub 2. Because if a function dies off at 1 and stays at the x-axis, well then it's at the x-axis from 2 on. And then I sub 2 is contained inside of I sub 3, which is contained inside of I sub 4, and so on and so forth. And clearly, this doesn't stabilize either, because you can always just take a function that doesn't zero out until it has to, and that's going to be in the next stage, but not in the previous stage. Okay, so there we've got it, 2 non-examples of rings satisfying the ascending chain condition. Now I'd like to prove that all PIDs satisfy the ascending chain condition. But in order to do that, I'd like to do an example of that happening first, which is to show that the integers satisfy the ascending chain condition. And the reason we want to do that is because a lot of the techniques used to prove things about PIDs in general can be adapted from the proofs that we see in the integers. Okay, so now we're going to show that the integers satisfy the ascending chain condition. Let's recall that we know from a previous video that z, the integers, is a PID. In other words, every ideal is principal. Let's also observe that via something pretty similar to a homework exercise, we know that the ideal generated by A is a sub-ideal of the ideal generated by B if and only if we have B divides A. Okay, well, now how would we show that? Well, notice that here we have little a is inside the ideal generated by B, but that means that little a is equal to B times Q for some integer Q, but then that's exactly the same thing as saying that B divides A. So that's a little sketch of this. You could like fill in more details or flesh out this argument if you want to, but I think it's pretty clear that we've got that kind of relationship here. And in fact, the correct way to generalize divisibility like this is by containment of ideals, just kind of FYI. All right, so now how are we going to jump to this main result where Z satisfies the ACC? Well, we're going to do it by way of contradiction. So by way of contradiction, let's suppose we have some integers. I'll call them A1, A2, so on and so forth, all integers, such that the ideal generated by A1 is contained inside of the ideal generated by A2, but not equal to, which is contained in the ideal generated by A3, but not equal to, which is contained in the ideal generated by A4, but not equal to, and so on and so forth. So in other words, we've got this infinite chain. All right, nice. And then I'd like to point out that without loss of generality, we might as well assume that all of these AIs are bigger than or equal to 1. Well, and why is that? Well, simply because the ideal generated by, for instance, -4 is the same as the ideal generated by 4. I think that's pretty clear. Okay. But now let's apply this divisibility condition that we saw up there to this big string of ideals and see what that gives us. So let's observe that we have A2 divides A1. I think that's pretty clear. And then A3 divides A2, and then A4 divides A3, A5 divides A4, and so on and so forth. But now what I'd like to do is take that divisibility and write it as an inequality. So let's observe that if A2 divides A1, that means we know that A1 is bigger than A2. You might say, well, maybe it's bigger than or equal to A2 because these could be equal. But if these were equal, then the ideals would be the same, but we're assuming the ideals aren't the same. And we know both of these are positive, and since both of these are positive, that gives us this inequality like this. If one of these were negative, we wouldn't quite have the inequality like we have it, but over there we're assuming, without loss of generality, that these things were positive. Okay, but then let's notice this A3 divides A2 means that A2 is bigger than A3. We know that A3 is bigger than A4. We know that A4 is bigger than A5, and so on and so forth down the line. But now this is going to pretty quickly bring us to some sort of issue. So notice that if A1 is bigger than A2, that tells us that A1 is bigger than or equal to A2 plus 1. We just add 1 here, and it may not be bigger than anymore, it may be equal to. And then the same kind of thing here. So this means that A2 is bigger than or equal to A3 plus 1. But now we can push these two lines together, and that's going to give us A1 is bigger than or equal to A3 plus 2. And then now we can push down here to see that A3 is bigger than or equal to A4 plus 1. And now we can take these two to show that A1 is bigger than or equal to A4 plus 3. And then, well, we can push this one down here to say that A4 is bigger than or equal to A5 plus 1. And then we can take these two to show us that A1 is in fact bigger than or equal to A5 plus 4. And then I think generally it's pretty obvious that we have the following relationship, which you could prove carefully with induction if you wanted to, and that is that A1 is bigger than or equal to A sub n plus 1 plus n, and this is true for all natural numbers n. But of course, that's impossible, right? Because that tells us we've got a natural number A1 that's bigger than every natural number. But of course, there is no natural number bigger than every other natural number, so that brings us to a contradiction. Okay, nice. So now let's move on to this general result that I alluded to, where every PID satisfies the ACC. All right, so now into this big result. So let's suppose that D is a PID, and we've got this ascending chain of ideals. I1 is contained in I2, which is contained in I3, and so on and so forth. Now we want to show that that chain stabilizes somewhere. So now here's what I'm going to do. I'm going to set capital I equal to the union of all of those ideals. So that's going to be the union as k goes from 1 to infinity of I sub k. And now, a priori, we do not know that that is an ideal, but we're going to show that it's an ideal. Now, perhaps it shouldn't be super obvious that it is an ideal, because we know that if we take the union of two ideals, we need not get an ideal. Versus if we take the intersection of two ideals, we do get an ideal. But anyway, let's show that this I is an ideal. Okay. So how can we do that? Well, let's recall that we had something called the ideal test, so we can use that. It needs to be closed under subtraction, and it needs to have this absorption property. Okay, so let's suppose that I and J are in I, and maybe little a is in D. But now let's observe that that means that I is an element of I sub m and J is an element of I sub n for some natural numbers m and n. That's just what it means to be inside of a union, right? It's inside of at least one of them. And now, without loss of generality, I'm going to go ahead and assume that m is less than or equal to n. Okay. But now note that we have the following. So let's note that I is inside of I sub m, which is contained inside of I sub m plus 1 all the way up to I sub n because of our chain. But that means that I minus j is inside of I sub n because they're both inside of I sub n, and I sub n is closed under subtraction because it's an ideal itself. But then I sub n is contained inside of I because it's one of the terms in the union. So that's all it takes to show this is closed under subtraction. Now we've got to show that it has the absorption property, but that's pretty easy as well. Notice that we know that A times I is inside of I sub m, and that's because I sub m is an ideal. It has the absorption property, but then that's a substructure of I. So that means A sub I is inside of I. And notice that we don't need to check I times A because we're in a commutative ring. So we have commutativity of multiplication. Okay, so now we've got this thing is an ideal. So let's just put here that this is an ideal. And I'm just going to put a check mark next to this to show that we've proven this. And then let's erase the proof and then do the rest of our main proof here. All right, so we know that this union of all of the ideals in the chain is an ideal in our commutative ring. Notice we haven't used any information about this being a PID yet. So now we want to do that. Okay, so since D is a PID, that means that there exists A sub k inside of D such that I sub k is generated by A sub k. Because every ideal is principal, so we're just taking all of those ideals and writing them as their generator. But then also, we know that the big ideal I is generated by a single element as well, and that's because, again, we're inside of a PID. There's nothing really fancy going on there. Okay, nice. But now let's note the following. So let's note that A is inside of I because, well, A is generating I, so it's definitely inside of I. But then I is equal to the union as k goes from 1 to infinity of I sub k. So that means A is in this union, but that means that there exists, let's see, a capital N inside of the natural numbers such that A is inside of I sub capital N, but notice that that is the ideal generated by A sub capital N by our kind of assumption up there. Okay, so now let's observe the following. So let's observe for all little n bigger than or equal to capital N. So I named that capital N to be suggestive. We have the following. So we have I, this capital I, which was this union of ideals, is equal to the ideal generated by A, which is contained inside of the ideal generated by A sub n. And that's because this little a is in the ideal generated by A sub n. So that kind of goes without saying, but that's equal to I sub capital N. But then that's contained inside of I sub little n, because little n is bigger than or equal to capital N, and we've got our chain. But that's contained inside of the union of all of these, but that's equal to our I. So notice that what we've got here, we've got this subset containment kind of thing, and we've got the same object on either side of it. But since we've got the same object on either side of it, that means that everything in this chain of containment and equality has to be the same. In other words, that means that these two objects are the same. So in other words, we have I sub n is equal to I sub capital N for all n bigger than or equal to capital N. But that's where we wanted to end up for this to satisfy the ACC. So we've done it, every PID satisfies the ACC. In other words, every principal ideal domain is a Noetherian ring. Okay, so now what I want to do is show inside of PIDs, the notion of an irreducible element is the same as the notion of a prime element. All right, so now let's show that in a PID D, an element P is irreducible if and only if it is prime. So let's observe that in every integral domain, we've shown if something is prime, then it's irreducible. And maybe let's also recall that these have some precise definitions which will be illuminated during our proof. But if you don't recall those precise definitions, maybe look up in your notes from previous videos. Okay, so that means what we need to do is show that in a PID, if we've got an irreducible, then that irreducible is prime. And I'd just like to note, although it doesn't have any bearing on this proof, we've already shown that this is the case inside of a unique factorization domain. Okay, so let's get to the direction that we need to prove, so this forward direction. So let's suppose that we've got P inside of D and it is irreducible. Okay, so now what are we going to do with that? Well, of course, we're going to need to form some sort of ideal and take a principal generator for that ideal. And that is because we're inside of a PID. We've got to use the fact that we're in a PID. But we also have to work towards the definition of a prime element. So let's do that by saying that P divides A times B. And we're doing that because what we'll want to show is that P divides A or P divides B. And that's because that's the definition of a prime element. If P divides a product, it has to divide one term of the product. That was the definition of a prime element inside of an integral domain. Okay, so now let's consider the following ideal. So it's going to be generated by P and A. So it's generated by two elements. But it's not only just generated by two elements. Since we're in a PID, it's generated by a single element. Let's call that single element D. So we're able to bring that single element into existence because we're in a PID. All right, so now we're going to kind of break this into a couple of cases. So let's look at this first case. So if D is a unit, let's see what happens. So that means that we have the ideal generated by P and A is equal to the ideal generated by D, which is equal to the whole integral domain. Probably in a previous homework exercise or other exercise that we've done for this class, or maybe you should do this on your own if you haven't done this exact exercise, is show that if you take the principal ideal generated by a unit, you get the whole ring. And that's the whole ring, even if we're not inside of an integral domain. Okay, so anyway, so what does that tell us? Well, D contains the element 1. That's because it's an integral domain. It contains the multiplicative identity. So that means that there exists x and y inside of D such that P times x plus A times y is equal to 1. And that's because elements of this ideal generated by P and A are of the form Px plus Ay. And then again, 1 is in that because we had our previous discussion. Now what I'm going to do is take this equation and multiply it by B. So we'll have P times B times x plus A times B times y equals B. But now let's note that we have P divides AB, but that means that AB is equal to P times C for some C, if you will. But now I can take this AB that's right here and replace it with P times C. So I'm just going to put a P times C here, and then observe that I've got a term that's P in both parts of this left-hand side. So I can factor the P out, and I'll have Bx plus Cy is equal to B. But now this equation right here is, well, part of the definition for P to divide B. All right, so that means in this setup where D is a unit, we get that P divides B. And that was one of the things that we wanted to end at. So of course that means that we want to show that if P is not a unit, then P must divide A. So let's get to that. All right, so we just noted that in this case where the ideal generated by P and A is equal to the ideal generated by D, if D is a unit, then P divides B. Now we're going to assume that D is not a unit, and we'd like to end up with the other, requirement, which would be P divides A. Okay, so how are we going to do that? So if D is not a unit, then let's notice that since P is an element of the ideal generated by D. So I think that's pretty clear because observe that here, this thing right here contains P, but this thing right here is equal to this thing right here. So that means that ideal generated by D also has to contain P. But that means that P is equal to D times R for some R in our integral domain. Well, that's what the ideal looks like. It's all multiples of D. But notice that that means that R is a unit. Now, how do we know that? Well, observe that P is irreducible, and we factored it as two things, one of which is not a unit. But let's recall, if we factor an irreducible into two pieces, one of those pieces has to be a unit. We've got this assumption right here that D is not a unit. That means that R is a unit. But now let's observe that that means that D is equal to P times R inverse. We can simply multiply by the multiplicative inverse of R because R is a unit. Okay, nice. But now let's observe this means the following, and that is that D is in the ideal generated by P. All right, so now let's see how this is gonna go. So let's observe that A is an element of the ideal generated by D. Well, because A is one of these generators here, this is the principal generator. But then, since D is in the ideal generated by P, this is also inside of the ideal generated by P. In other words, A is an element of the ideal generated by P, but that means that A is equal to P times X for some X in D. That's what it takes to be inside of that ideal, but let's quickly observe that that means that P divides A. So check it out. We've done it. If D is not a unit, P divides B. If D is a unit, P divides A. That means we've started here. P is an irreducible and a PID. It divides A times B. That means it must divide one of them. But that's the definition of P being prime, so that means we've proven this theorem. Okay, so now we're going to jump into our big proof that every PID is a UFD. Okay, so now we're ready for our big result, that every principal ideal domain is a unique factorization domain, or shortened, every PID is a UFD. So we're going to prove this using 3 steps. The first step is to prove that every non-zero non-unit has an irreducible factor. Then after that, we'll prove that every non-zero non-unit can be factored into irreducibles, and then we'll prove that that factorization is unique. Okay, so let's jump into it. So we're going to start by taking a non-zero non-unit. So I'll call that A naught. So here we've got it's not equal to 0, and it's not a unit. That means it does not have a multiplicative inverse. Okay. Now, let's observe the following thing that kind of just gets this off the ground. If A naught is irreducible, we're done. That's because if it's irreducible, then it's kind of an irreducible factor of itself. Okay, so now let's move on to the next case, which is if A naught is not irreducible, then we can write A naught as B1 times A1, where these are both non-units. So B1 and A1 are non-units. Let's recall that something's irreducible if, when you factor it, it necessarily factors with a unit. So if we've got a non-unit, then that means when we factor it, we can factor it into 2 non-units. Okay, nice. But now I think we can kind of see where we're going just by the numbering here. We started with A naught, that's like our seed, if you will. Then we're producing B1 and A1. And so now we're just going to repeat this process. So we would repeat this process with A1. Remember, that's a non-unit. And we'll write it as like B2 times A2. So let's just point out what we're doing here. So let's repeat to create this list of elements AK, BK with A sub n equal to B sub n plus 1 times A sub n plus 1. Okay, so now we're gonna break this into two possibilities as well. So if we hit an irreducible along the way, then we're done, and we have an irreducible factor of our original A naught. So let's get that written down. So if we hit an irreducible, I'll call it AN, then we have the following. So we've got our A naught can be written as B1 times B2 all the way up to B sub capital N minus 1 times AN. So that means that A sub n is an irreducible factor of our element A naught, kind of as needed. And so check it out. If we hit this A sub n, which is irreducible, then we have a factor that is irreducible of A naught, which is what we wanted to show here, that every non-zero non-unit has an irreducible factor. So if we get down to this point and we hit an irreducible, we've got a irreducible factor. Okay, so now let's look at the other case, which is if we never hit an irreducible. So I'll just write it like this. If we never achieve an irreducible, then we have a chain of ideals. So of ideals that can be written like this. So we've got A naught, which is an ideal that is not equal to the ideal generated by A1, which is contained in but not equal to the ideal generated by A2, which is contained in but not equal to the ideal generated by A3, and so on and so forth. So we've got this proper containment of ideals. So let's just briefly see that we have A naught is equal to B1 times A1, but that means that A naught is in the ideal generated by A1, but that means the ideal generated by A naught is a sub-ideal of the ideal generated by A1. Then we know that it's a proper sub-ideal because B1 is a non-unit. Let's recall that previously we proved that principal ideals were equal if and only if they were generated by associates. So this is saying that these are not associates, so that means we have a strict containment and not equality. But let's observe what we have here. We've got this increasing chain of ideals that never stabilizes. We know that it never stabilizes because we never achieve an irreducible, so we can keep doing this factorization. But look, that contradicts the fact that principal ideal domains have this ascending chain condition. The ascending chain condition means that we cannot have this infinite ascending chain of ideals that does not stabilize. Okay, so that means that this case down here was impossible, which means this case is the only possible case. In other words, we achieve an irreducible after this iterative process, and that irreducible is a factor of our original element. Okay, so now we've proven this first step. Now let's move on to the second step. And that next step is to prove that every non-zero non-unit factors into irreducibles. So let's start by taking a non-zero non-unit, so we'll call that A. That's from our PID, which we've called D. And let's write the following. So let's write A as maybe P1 times A1, and that is where P1 in D is irreducible. Okay, so notice that we used the first step already to produce an irreducible factor of A. That irreducible factor of A is P1. And now we're going to kind of do the same thing that we did on the previous board. We're going to continue this process. So I'll just put here, let's again continue. And that continuation will produce these equations AK, which is equal to PK plus 1 times AK plus 1, where PK is, or maybe where the Pn are all irreducible. Now, of course, we may have to stop at some point because one of our A's is irreducible, or we may get to continue forever. And that's where we're gonna take our next step, which is pretty similar to that step that we had on the previous part of this proof. Okay, So let's say, so if we achieve a unit, so in other words, one of our A's is a unit, I'll call it A sub n, which is U, then we have the following equation, which is really a factorization of our original. So we have A is equal to U times P1 times P2 all the way up to P sub n, and that means we're done. We've got a factorization of A into irreducibles. Well, an irreducible times a unit, but inside of a UFD, that is essentially the same thing as factoring into irreducibles. Okay, in fact, we can really think of U times P1 as just being an irreducible, which is an associate of the irreducible P1. Okay, so that's this first case. So this second case is if we never achieve a unit. So if we never achieve a unit, then we create a non-stabilizing chain of ideals that looks like this. So the ideal generated by A1 is going to be contained but not equal to the ideal generated by A2, which is contained in but not equal to the ideal generated by A3, and so on and so forth. So in other words, like I said, we've got this infinite non-stabilizing chain, but that's a contradiction because since we're in a PID, we cannot have an infinite non-stabilizing chain. So that means this is an impossibility, which means this process that we've outlined at the beginning of this step eventually achieves a unit, which gives us a factorization. Okay, so now we've proven that every non-zero non-unit factors into irreducibles. Now what we have to do is prove that this factorization is unique. Okay, so now we're going to show that factorization is unique, and this is actually pretty similar to the way that we show factorization is unique in the fundamental theorem of arithmetic inside of the integers, and the way we did it when we showed that the polynomial ring over a field f adjoin x was a UFD. And that's because all of these, or you can think about this proof as a generalization of those two proofs. Okay, so we're going to start by taking an element A and writing it as a product of irreducibles. So we've got this product P1 up to Pm and Q1 up to Qn. We might as well assume that m is bigger than or equal to n, because one of those has to be bigger than or equal to the other. And then Pi and Qj are irreducibles, but let's recall we just proved that irreducibles were primes inside of PIDs. So we're going to use that. So now let's note the following, which will get us off the ground. So P divides A, but that means that P sub m divides A, because it's this term in the product right here. But that means that P sub m divides this product Q1 up to Qn. Now, we know that if P a prime divides A times B, it has to divide A or it has to divide B. Well, now we're going to apply like an inductive version of that to say that if a prime divides this product of n things, it has to divide one of them. And I'm going to leave that little thing as an exercise to prove that this is possible via induction. So I'm just going to say here, that means that P sub m divides Qk for some k between 0 and n. Sorry, between 1 and n. Now what we're going to do is reorder the terms on the right-hand side. So we're going to shuffle around the ordering of Q1, Q2 up to Qn so that we have P sub m divides Q sub n, so that the one that is divisible by P sub m is the last one. But now let's observe that means that Q sub n is equal to some element C times P sub m. That's what it means to be divisible. But let's recall that Q sub n is an irreducible or a prime element. That means that this C is in fact a unit. So I'm going to introduce that notation here. So write C equal to U sub m, and I'll just point out that that is a unit. That's because anytime you factor an irreducible, one of the terms in that factorization has to be a unit. We know that P sub m is not a unit because it's a prime, so that means that the C has to be a unit. Let's rename that thing U sub m. So now our equation looks like this. So we have P1 times P2 all the way up to Pm minus 1 times Pm is equal to U times Q1 times Q2 all the way up to Qn minus 1 times P sub m. What I did there is I replaced my Qn with my unit U, well maybe we'll call that U sub m times P sub n. But now what I can do is simply do a cancellation because we're in an integral domain. We don't need anything other than being in an integral domain to do a cancellation of this P sub m factor on both sides of the equation. But now observe that we've just set up some sort of induction if you wanted to do this more carefully, or I'll just say that we could continue this process until we get the following type of product. P1 times P2 all the way up to Pm minus n, because what we're doing is we're taking something at the end of the right-hand side and showing that it's an associate of something at the end of the left-hand side. So eventually you're going to end up with m minus n terms on the left-hand side. And then on the right-hand side, you're going to have this product that looks like this. U sub m times U sub m minus 1 all the way down to U sub m minus n, but that's equal to U, which is a unit because it's a product of units. But if you've got a product of irreducibles, which is a unit, well, that means that you have an empty product over here, which means there are 0 terms in this product, but 0 terms being in that product means that you have m equal to n. But that's all we need for this unique factorization to have occurred. Notice we show that the factorization is into the same number of irreducibles, and we showed that those irreducibles are associates. So notice that we have Qn and Pm are associates. And since we know that m is equal to n, we actually know that Q sub m and P sub m are associates. Okay, so we've done it. We've shown that every PID is a UFD. So now what I want to do is give you an example of a UFD that's not a PID. And we're just going to hand wave the reason why and probably prove it more carefully later. Okay, so for our example, we'll see that Z adjoin X, polynomials with integer coefficients, is a UFD but not a PID. And here's a sketch of how it goes. So let's take a polynomial f of x inside of z adjoin x, and we can view that as a polynomial in q adjoin x. In other words, we'll just view those integer coefficients as rational coefficients. But recall that q adjoin x, because q is a field, is a PID, which implies it's a UFD. I guess we proved that it was a UFD directly, but we also proved that it was a PID, and now we can use that last theorem to immediately have another way of seeing that it's a UFD. So anyway, now we can factor f of x into irreducibles over q adjoin x. And so I'll call those irreducibles pi tilde of x. But then let's recall that a factorization in q adjoin x gives us a factorization in z adjoin x. That's something that we proved in a previous video, and that means that we can replace all of these pi tildes with just pi's. So that means you've got f of x is equal to p1x times p2x all the way up to pnx, where those pix are in z adjoin x. And then, I guess you have to argue a little bit that all of those pi of x are irreducible polynomials in z adjoin x, but I'll let you fill in the details for that, or maybe look it up in a standard textbook. So anyway, we've got a unique factorization. Now what we want to do is recall that this ideal generated by 2 and x as an ideal of z adjoin x is not a principal ideal. So we've got an ideal which is not principal, which means it's not a PID, and we've got a unique factorization property, which means it is a UFD. So while all PIDs are UFDs, not all UFDs are PIDs. So now I'm going to leave you with some exercises. Okay, so here are 2 exercises. So the first is the one I alluded to in that proof that we saw, and that is, let's let P be a prime in an integral domain. Now, of course, we were inside of a PID and we were talking about irreducibles, but all irreducibles are primes inside of a principal ideal domain. And so this is like slightly more general. You just need a prime element in any integral domain. And that prime, let's suppose it divides this product A1 up to AN. Then what you want to do is prove by induction or otherwise that P divides A sub I for one of those i's between 1 and n. The next little exercise is really just a gut check if you remember some of the examples we've seen throughout these videos, and that is to fill this following diagram with examples. So notice we've got increasing structure as we move from left to right. So over here we have a ring, a commutative ring with one, an integral domain, a UFD, and a PID. And your task is to fill in each of these with the maybe least structured object possible. So in other words, what would go here is a ring which is not commutative, a commutative ring without identity, a commutative ring with identity that's not an integral domain, and so on and so forth. And that's a good place to stop.